Chris, you tell me when to start because I don't know.
I think you can go. Yeah.
You can go? Okay, so welcome back, everyone. This is, I guess, the very last part of this 3-day workshop, which was super fun, as a matter of fact. So this is a round table on varieties of realism in quantum physics, and we have Alexia, Chris, and Wayne. So you have, as I said, you have 15 minutes each, I mean, or whatever you want. Then you can comment on each other, and then I'll open the discussion. I'll just start with Alexia alphabetically, if it's okay with you. So Alexia, you take it away.
Okay, so let me share screen. And that's it. Can you see my screen here?
Yes.
Okay, great. So yeah, so that's basically the title of my presentation, where the goal of these discussions that we are going to have is to make obvious that here we have two kinds of possible ontologies, one that I would call object-based and one that I would call relation-based, and that quantum phenomenology doesn't make these two ontologies equivalent. So that's basically what I would like to comment here. And I'm going to spend a few minutes to set up the stage and first stating the obvious, basically. So it starts with a few considerations, a small ontological experiment that you can do in front of your computer. You can look at your computer and close the eyes, open the eyes again, and you see your computer again, close the eyes, open the eyes, see your computer again. So now Morpheus asks you, what makes you suppose that basically your computer exists? And then you are Neo, and you try to build some logical argument. So you say, okay, I made the experiment many times. I open my eyes, I close my eyes, I see the computer. So there is a repetition of my experiment and my perception. And then I can also call Trinity, and Trinity will also be able to check that there is a computer in there. So there is an agreement between parties. And this repetition, this agreement between parties, this makes you think that basically this computer exists. And more than that, this computer exists even if no one is watching. So that computer is objective. It is real. But then Morpheus can ask you, but can you demonstrate this? And then if Neo is smart, and I guess he is, he realizes that he's not able to answer this question. So this is a very important message that probably all of you are aware of, the fact that ontology is always postulated. And I'm adding a bit of physics here. Ontology can be seen as the most efficient model to account for the patterns in our perceptions. And this argument I'm going to develop in the next few minutes. But first, I want to precise what I mean by pattern. Patterns are correlations. And typically, the experiment, so now we can develop a bit on the experiment that Morpheus is doing with Neo. Morpheus has one pill in his hand, but Neo doesn't know if the pill is red or blue. So Morpheus opens his hand, and then Neo sees that the pill is blue. And then Morpheus can do the experiment many times of closing and opening his hands. And then Neo will keep saying B, 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 like the pill is blue. So that's the repetition. And repetition, phrased in physical terms, this is a temporal correlation between an agent perception that when we can call measurements, okay? And phrased in even more statistical terms, we can say that if Neo first sees that the pill is blue, then you always see the pill is blue. So we get a certain perception that is conditioned to the first one. Now, one step further, Neo and Morpheus can compare their perceptions, and they reach an agreement, which is nothing but also a correlation, but now between two agents' perceptions. And if Neo first sees the pill as blue, then Morpheus will. So we have something more that conditions to Neo's perception, Morpheus' perception will be certain. So starting from these very obvious considerations, I want to investigate what is the ontological status of these correlations. And there are basically two options I want to present. Either correlations emerge from objects, and this is what we can call object-based ontology, or objects emerge from correlations, and in the end of the day, we don't care about objects, and this is what we can call relation-based ontology. So first case, imagine I'm going to present the argument for the fact that correlation emerge from objects. That's a possibility. So what do people do? Again, they compare their respective perceptions, they see that there are correlations, and they explain these correlations by postulating a fact, the fact that the pill is blue. Doing so, this is a very strong act, that's a postulate. They postulate that the pill exists and that it is blue, and that would be so even if no one is observing it. So that's objective reality. But there is something more. There is also the fact that any other agent would see the same blue pill if he were to do the experiment. So for instance, here, Trinity comes and can check that the pill is blue. So the cost of this approach of ontology is to postulate that there is an objective reality. But the gain is that we gain one single cause for many correlated perceptions. So if I phrase this in terms of machine learning, this is a very efficient model because we eliminate redundancies. We don't need the information spreads over the head, Neo, Morpheus, etc. We just have one cause, so we save memory. This is an efficient model. The other very important thing that we gain is that it provides trust, because any agent will be able to come back and check the facts at will. And this is actually something very important that I want to insist on, which is the fact that facts matter. And it's the basis of scientific reasoning. Facts, I define them as postulates from intersubjective and reproducible perceptions, and fact can be checked by any agent at will. So this object-based ontology, it can really be seen as a reservoir of fact, okay? And this is extremely important because I'm a physicist, I'm also a citizen, and we know from recent history that fact matters. So if you don't value facts, then history can be very different. So now you know on which side I am. I try to be agnostic with respect to the type of ontology, but I'm quite an object-based ontology person. But then I want to defend the other point of view, or still to embrace the other point of view. So the other point of view is the following. In the end of the day, we have no proof that objects exist. The only thing that we can observe are correlations. So correlations are basically the substance of reality, and they do not need any object as a substrate. And this is basically the tenet of relational approaches, as much as I understood them. So the gain is basically the absence of cost, because I don't have to postulate anything. There is no need to postulate any external reality. And there is also no need to postulate either perceiving entities or agents, because the correlations, they can take place between physical systems that don't think. So that's quite good. Actually, this kind of ontology can pretend to be more objective than the object-based ontology, because we don't need agents anymore. So what is the cost? The cost is high as far as I'm concerned, as far as I feel it, because you don't have any more facts in the sense that I defined above. And reality in that sense becomes kind of a collection of mirrors where Morpheus is there is a fact for Neo, but Neo is there is a fact for Morpheus. And then Morpheus knows that Neo is there is a fact for Trinity. And all over the place, there are only relative facts. So facts are relative. And if I put Trump in the slide before, it's for this reason, because for me, this really sounds like alternative facts. So even if this ontology is extremely interesting, I think we must pay attention to the language that we use and what we propagate to the society. So I close the parenthesis, the political parenthesis. So here is a summary. We have two poles, basically. We have correlations and we have objects. And there, either we choose to be in the relation-based ontology type, which means that we think correlations are more fundamental than objects, and correlations are the ultimate and intimate substance of reality. Or we can choose the other approach, which is to use some sort of hypothetico-deductive approach. We choose to model reality with objects that can then explain the correlations, and that's the choice of object-based ontology. Last bit of comments on this. In the classical realm, actually, measurements are harmless. So new correlations can emerge between physical systems, and these correlations, they won't alter formerly established correlations. And this is very important because actually, there is no way to distinguish between the two approaches. Basically, they are kind of equivalent. You can live your life without really asking the question of which one is more or better than the other. In the quantum realm, it's becoming more difficult because, as you all know, measurements disturb. And there is the no-cloning theorem. And this no-cloning theorem induces some sort of lift of degeneracy between the two types of ontologies. And so the game would be to find a third path or a synthesis. And that will be my last slide, which is a slide of advertisement for the position that we have been funding with Philippe Gangier and Naila Farouki for a few years now, which is called the CSM ontology, like context, systems, and modality, where we basically try to get the best of the two worlds. In what sense? So in the CSM ontology, we do have systems that interact with contexts, and contexts are basically the place where objective facts can emerge. So this is an object-based ontology. And the good thing is that we get the trust, we get the advantage that we can trust facts and trust each other and build science with it. At the same time, we do have these facts here that depend on the system-context relations. So in this approach, modalities, well, properties that we call modalities, they are relational. So which is important from the other type of ontology. And then we don't need agents anymore. So I'm happy to tell you more if you're interested. And this was the last slide of my presentation. I actually absolutely don't know how much time it took. Well, I think more or less on time.
It was absolutely perfect, actually, on time. Thank you so much, Alexia. So we will slide over immediately to the other talks and then move back to discussions. Christopher, you're up. You're muted. You're muted, Chris.
Now I'm unmuted. It took me a while to figure it. So hopefully, and finally that. Good. So as many of you know, there's been a historical tension between Cubism and philosophers of science, and I tried to depict that historical tension with this picture of Pablo Picasso and his gun. Being a Texan, I sometimes feel I have to carry a gun into philosophy meetings myself. If I were to characterize the experience I've had with philosophers of physics, and I emphasize philosophers of physics, not necessarily pragmatists or phenomenologists, over the last 20, 25 years, it would be that their reaction is, wah, you're not realist enough for us. The way Cubists think instead is that it is the world that decides which philosophy best fits it, not the other way around. We took a gamble that an epistemic view of quantum states was the best road to progress and followed the consequences of that. We figured nature, not fellow philosophers would let us know if we were on the right track. So we busied ourselves doing what we do, building a consistent picture, proving theorems, methodically dissecting the theory, and it's been a long, hard road. But particularly, I'd like to emphasize that instrumentalism or anti-realism was never a presupposition of the project. Cubism has always seen itself as a methodology for unearthing an ontology. An ontology is the end goal of all our efforts. We took guidance from Ed Jaynes at the very beginning, and it really hasn't changed much since then. Jaynes said sometime in the 80s, our present quantum mechanical formalism, I put that in purple, is a peculiar mixture describing in part laws of nature, in part incomplete human information about nature, all scrambled up together by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet we think the unscrambling is a prerequisite for any further advance in basic physical theory. That impressed me much in 1993, and I embarked on the process of trying to unscramble the omelet. One thing struck me particularly strongly one late night in 1995, when I appreciated for the first time that following Jaynes's quest could create new physics, or at least it could pressure new physics into existence, or new physical considerations into existence. Particularly in that late night, something struck me. I said, wait a minute, what's so quantum about the quantum no-cloning theorem? I had been studying Asher Perez's book, and he impressed upon me some things about Liouville mechanics. Consider the way the no-cloning theorem is often presented, for instance, on Zurek's webpage, where it says, Zurek also demonstrated with Wouters that an unknown quantum state cannot be cloned. This is a fundamental result in an essential distinction between classical and quantum. What struck me that night was, indeed, you can clone states classically, you can clone the ontic states. But if you speak of the epistemic states, Liouville distributions on a phase space, then Hamiltonian mechanics will not let you clone them either. It was only a prejudice that quantum states should be thought of ontically that made it look like a big deal. Well, that led to a new question. Is there anything uniquely quantum about the no-cloning theorem? And there wasn't, but a generalization of it that we call the no-broadcasting theorem that involved entanglement was uniquely quantum, and it involved the idea of non-commutivity. I put here that it has 685 citations on Google Scholar as of this morning, just to point out that if this were only foundational work, and it was only foundational work, if this were only viewed as foundational work, it would not have that many citations. Doing foundational work could lead to genuine physics. Here's one more example. In the late 90s, I started thinking unknown quantum states. Everything in quantum information is about unknown quantum states. But from our point of view, from the point of view we were trying to develop, that a quantum state is a state of knowledge at that time, this must be an oxymoron. What can it mean for a quantum state to be unknown if it's a state of knowledge? After a lot of thinking about it, the solution seemed to call for something that I'll call a quantum definiti theorem. But what if it couldn't be proved? This would be the acid test for our game. If you couldn't prove something like a quantum definiti theorem, then maybe this whole conception of epistemic states was wrong. It didn't have to be necessarily provable. For instance, it fails if quantum mechanics is based on real vector spaces. And it fails if quantum mechanics is based on quaternionic vector spaces. But in fact, you could prove it in complex vector spaces. And this gave the cubist a notion, or the proto-cubist a notion of how to answer the question, what is an unknown quantum state? I could tell you a number more things like this. Main thing I want to impress upon you is that a physicist says, if I have a point of view for exploration, and it's productive, don't just stop and say, wah, 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 it can't be right. you proceed and see if it leads somewhere. So particularly, I want to talk about something that I consider the holy grail of the Cubism research project right now, and that is recasting the Born rule and unitary evolution, the Schrödinger equation, both in full-blown Cubist terms. It turns out this has spurred a huge amount of mathematical physics in the form of something called the SIC-POVM problem, which I'll tell you about in a little bit. It's a 20-year-old question now, and it's still not solved. But what I want to show you is that if it could be solved, it would teach us something about physics, and it would teach us something about where to proceed toward an ontology that underlies this Bayesian way of thinking of quantum probabilities. That point of view, I'm going to float the term today, is something I'll call normative structural realism, and it captures one aspect of the pieces of realism that Cubism is aiming for. It'll also help us give a response to Harvey Brown. A few years ago, he wrote in one of his papers, "Powerful plausibility arguments have long been available, some since the birth of quantum mechanics, to the effect that the quantum state is something real. They almost all have to do in one way or another with quantum phase, with the fact that the wave function in its relation to probability is a complex probability amplitude. It has more structure than a probability distribution does." What I'm going to argue is that's just simply not true. What Harvey is speaking about is an artifact of a particular formalism. And if you find a new formalism, you can get rid of the complex amplitudes. And in fact, you can get a formalism that's only in terms of probabilities. So the arguments that a quantum state has more structure based on complex numbers doesn't cut it. Toward this end, I'm going to go back to something Richard Feynman said in a 1951 paper titled The Concept of Probability in Quantum Mechanics. Feynman said, "The new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable, and that in these cases, one has to be satisfied with computing probabilities of various outcomes. But far more fundamental was the discovery that in nature, the laws of combining probabilities were not those of classical probability theory of Laplace. The laws of combining probabilities were not those of classical probability. What has changed, and changed radically, is the method of calculating probabilities." Of course, Feynman was thinking about the double slit experiment. And as he said in 1964, he said, "We choose to examine a phenomenon which has in it the heart of quantum mechanics. In reality, it contains the only mystery." Well, that was jumping the gun. As many people have pointed out, and as all of the analysis of Bell inequalities and contextuality results in Cushing-Specker have taught us, that was certainly jumping the gun. But I want to salvage an idea from Feynman, and that is that we can consider something like the double slit experiment. And think of it this way. If I perform the experiment without making measurements on the slits, I get an interference pattern. But if I make measurements on the slit to see which way the electron went, the interference pattern gets erased. We can think of this as an expression of the connection between three distinct experiments, measuring the particle here, measuring the particle here, measuring the particle there, and they're connected by introducing an ancillary notion, that of an amplitude. Let me generalize that. I'll call this the d-squared non-orthogonal slit experiment. And in this way, using the tools of quantum information, I can make it a general statement about how we calculate probabilities. So what you see before you is one measuring device followed by another. You can think of this measuring device as being analogous to the screen at the end of Feynman's. And you can think of this measuring device as analogous to measuring which slit the particle went through. We have to add a little more structure, a lot more structure, in fact, than Feynman did, Particularly, I want to make this measurement, the one in the middle, a minimal informationally complete reference measurement. So what I mean by that is I'm imagining finite dimensional quantum mechanics. And so let's say we have a Hilbert space of dimension D, and we're going to fix once and for all a measurement that we'll think of as a reference measurement. It'll never be changed. This is like choosing a coordinate system, a global coordinate system, say for space-time, when you can. The other measurement, on the other hand, is variable. It can be anything you want, not fixed at all. So let's consider how these probabilities, the probabilities for the outcomes of this measurement and the conditional probabilities for this measurement given the first measurement, and the overall probabilities for this measurement, how they're connected. Well, I've drawn in quantum states. An initial quantum state goes in rho, and a quantum measurement is performed, and then out comes a new quantum state, perhaps given by Luder's rule, and then it goes to the next measuring device. Suppose I erase the quantum states and leave only the probabilities. So I've erased the quantum states from the picture. There's no rho here. There's no sigma I here anymore. Suppose that somehow I just have hold of the probabilities, P of Ri, P of Ej given Ri, and P of Ej. Then we already know how to calculate P of Ej regardless of quantum mechanics. It has nothing to do with quantum mechanics. We just use the law of total probability for this situation. Whether these were classical measuring devices or quantum measuring devices, it wouldn't matter. The law of total probability for personal Bayesianism is a law of thought, or you might say normative guidance for how agents should reason. And so this is a phrase I'm going to hinge on, and it's going to make connection to normative structural realism. For the personalist Bayesian, an agent, the law of total probability doesn't tell an agent which probabilities must go into the relation. It only says that they should fit together. If they don't fit together according to this law, then the agent realizes that he or she has been irrational in some way and needs to adjust some of her probabilities. Suppose I turn the off switch on the intermediate measurement. So now my particle just goes straight through. It has a quantum state rho comes through and it goes to that. Now our only guidance is the Born rule. So now we have to explicitly invoke the operator rho and the operator ej's to calculate the probabilities. But I want to ask this question: can we do better? Can we make it clear that this too is normative guidance, much like the personalist Bayesian views the law of total probability, but conditioned on the character of the world that we're immersed in? In other words, conditioned on some fact of nature, some feature of nature. That's not anti-realism. We're asking, how should agents reason in light of the world they find themselves in? Well, a simple manipulation can turn the Born rule into this form. Look at it now. The left-hand term corresponds to the experiment where the intermediate measurement was turned off. That was like not checking which slit the electrons went through in Feynman's. The right-hand side, on the other hand, refers to the alternative experiment where the intermediate measurement is turned on. This looks formally almost like this, the law of total probability. The only distinction is that there is an extra matrix, a real valued matrix in the middle of it all, right here. Importantly, quantum mechanics does not allow the matrix to be the identity. So you get, in very visceral terms, the distinction between the Born rule and the law of total probability. It's that a certain matrix cannot be the identity. Nota bene, if you take the final measurement to be a unitarily Heisenberg evolved one as the reference measurement, this same formula provides exactly the Schrodinger equation. It gives unitary time evolution as well. So one formula captures the Born rule and the same formula captures unitary time evolution. Now, we cubists think that this is quite an important rephrasing of how probabilities are calculated, particularly because it leads to this question. If the Born rule is not the law of total probability, how close can it become to it? Well, that will depend upon what you choose as a reference measurement. We think we know what the answer is. It turns out that the measurement that we can find a measurement that lower bounds this quantity up here that's given by this. There's a simple symmetry condition that's required of its operators. So this is the Ri is the measurement operator, sigma I is the output state, so it uses Luther's rule, and we're demanding this nice symmetry condition. Trace Ri, Rj is equal to a constant whenever I is not equal to j. And in that case, the Born rule becomes this further variant of the law of total probability at the bottom of the page. So it takes a particularly simple form. Now here's the catch. Can you find a set of operators, Ri, d squared of them on a d-dimensional space that have this beautiful symmetry condition? For 20 years, people have been working on trying to prove that you can. There are examples now known all the way up to dimension 5,000, and every dimension between 2 and 193, I heard from Marcus Grossel the other day, has been shown to have a solution. But no one has proven the existence of these things. The existence question is a hard problem. So let me just give a summary of the Cubist way of thinking things. We now have this formula that we believe expresses the irreducible quantumness, the irreducible deviation of the Born rule from the law of total probability. What are we going to do with it? Well, first we're going to think long and hard on what it expresses about quantum reality. And the surprise, and the happy surprise, is, for God's sake, fulfilling the seek condition appears to be deeply related to Hilbert's still unsolved 12th problem. So this also means that the seek problem, this re-expression of the Born rule, would mean that algebraic number theory is deeply hidden within the potential representations of the Born rule. And now I want to ask this question. Could the Everettians or Bohmians, could they already know what quantum theory is all about? Could they really know what quantum theory is all about without taking account of surprising deep structural properties such as this? Ones that can reshape the formalism completely, ones that can take complex numbers out of the story and leave only expressions about how to combine probabilities. You see my answer, pa. Apparently it's a real word, I looked it up. So let me leave you with this thought. It's Erwin Schrödinger on responsible physics, to let you know this is how I think. In an honest search for knowledge, you quite often have to abide by ignorance for an indefinite period. I would say Cubism has been in a state of ignorance for a nearly indefinite period. Instead of filling a gap by guesswork, genuine science prefers to put up with it. And this not so much from conscientious scruples about telling lies, as from the consideration that however irksome the gap may be, its obliteration by a fake removes the urge to seek after a tenable answer. So efficiently may attention be diverted that the answer is missed even when, by good luck, it comes close at hand. The steadfastness in standing up to a non-liquet, nay, in appreciating it as a stimulus and a signpost to further quest, is a natural and indispensable disposition in the mind of a scientist. So I throw this out as my firing shot for talking about normative structural realism, what it has to do with the Born rule, and new ways of thinking about the quantum realism problem. Sorry for going over time.
No, don't worry. Thank you so much. This actually very provocative talk. By the way, before we give the word to Wayne, Christopher, I just want to say that some people have commented, Klaus, Chris, Timson, Aurilan have commented on the chat about R.V. Brown's argument for the reality of the quantum state. If you just want to look at the chat if you didn't have the time during the presentation. And Wayne, you're up next. Take it away.
Okay, thank you. I didn't really prepare a formal talk, and I only have one slide to show you because I wanted to make some very general remarks and in part be able to respond to my fellow panelists. And in fact, something Chris said during his talk fits very well with what I want to say. So he said, if I have a point of view that is productive, don't say, wah, you're not realist enough, pursue it and see where it goes. And I agree with that entirely. In particular, there has been, from fairly early days, a project of construing quantum states as something akin to classical probability distributions. And this is what Einstein thought. He explicitly compared quantum states to the probability distributions used in statistical mechanics. And, that project got dropped for a while, and I think to the detriment of our understanding of quantum mechanics, and then it got sort of revised. And the reason I think, and that project has given rise to very good work. So in particular, if you think about these things, one of the things you realize is you want to consider general properties of theories in which you're the best states that you have available to might be indistinguishable, and that might be built into the structure of the ontic state space, or it might be because you're dealing with probability distributions over overlap. And it turns out to be quite general that indistinguishable states cannot be cloned, and it does not matter whether they're built, the indistinguishability is built into the fundamental physics, or whether it's due to overlap on probability functions. And I think that in principle, people could realize that before the no cloning theorem, and then nobody would have ever thought of the no cloning theorem as something distinctively classical. And it motivates the idea of, okay, are there features of quantum mechanics that can't be reproduced in this way? And it gives rise to no-go theorems like the Barrett-Cavalcanti, Lau, and Moroni theorem that I talked about. Can indistinguishability, and Owen mentioned, can indistinguishability of quantum states be explained entirely in terms of overlap of probability distributions on an underlying state frame? No, they can't. So one of the things you learn about pursuing a project to see where it goes is sometimes you realize that a certain project cannot be brought to fruition, and that you've learned something. So this is very important, and I think that there's a tendency to prematurely close off potentially fruitful research programs. Now, I think going back to one of the things that I said on my first slide this morning, the question I've always been interested in is what, if anything, is the empirical success of quantum mechanics or quantum theory more generally telling us about the world we live in? It does seem to be telling us that the world is non-classical in some way, but what does that mean? What should we be telling us? And I said that I thought that we should strive to make any conclusions that we draw from it, including any ontological conclusions, be ones that are we have reason to expect to be reasonably robust, namely that they're not dependent on idiosyncrasies of the theory we have right now, or they're not dependent on the theory we have right now being exact, because we think it's not. And they're things that we can reasonably hope to survive successive theory changes. And in the philosophical literature, I've said things like this in papers a couple times, and in one paper I rather pompously called it the principle of metaphysical continuity. Right. So now in the philosophical literature on scientific realism, there's a standard response that says, silly philosopher, you don't know anything about the history of science. That's shown that that is impossible. And there's this argument that is sometimes known as the pessimistic meta-induction. And the basic argument goes, well, look, if you look at the history of science, it's basically been periods of complacency, where people thought they had things figured out, and then there's this revolution where everything gets overthrown. And there are all sorts of things that people used to think were fairly established about the furniture of the world, and we now reject. And we should, and then there's a, it's a meta-induction, because the idea is we should expect that to occur. Now, that's the sort of impression you get, I think, if you look at the history of science through very, step way back in a very oversimplified way. It's the sort of impression you get if you do a little bit of history of science. And if you start looking in detail at the actual episodes that people invoke, and my experience is any sense that that kind of argument has any weight at all vanishes. And here's why. You have to become cautious about what it is that scientists of the past were in fact committed to. And in general, yes, at any time there are parts, there are things that people regard as more or less speculative. There are things that people regard as fairly well established. And in general, I think that being clear about which is very important. My teacher, Abner Shimoni, had a nice slogan about these things. He said, Aristotle taught us that moral virtues are means between opposing vices. Abner says intellectual virtues are also. So we should, at one end is one vice is excessive skepticism, where you think you don't know anything and expect everything that you believe to be true to be overturned. And the other vice is excessive dogmatism, where you have too much confidence in your best current theories. And the path of virtue is a mean between those, which does justice both to what we are learning and to the limitations of it. Let me just say a little bit about what I mean when I say that if you look more at the history of science, that sort of pessimistic meta-induction seems not to wait. So one of the examples, so here's one of the examples that people often use is atoms. People used to think that atoms are indivisible, and then, hey, we found out that you can split the nucleus. Okay, and that suggests that there was this fairly long period when everyone thought atoms existed. They thought that was well established, and they were indivisible. Well, who is committed to them being indivisible? What Dalton says is he believes that atoms cannot be created or destroyed by chemical means. We agree with that. A nuclear reaction is not a chemical reaction. It's something else. If you look throughout the 19th century, there was no consensus at all, even among the chemists who are all using these atoms in their stoichiometric calculations. There's no consensus at all whether they should be thought as really existing things or as really existing things, or just things we use for note keeping purposes. It wasn't really until 1912, after Perrin's experiments on Avogadro matter, that anything like a consensus about atoms came to existence of atoms. And Perrin actually says, yes, and at the same time, we're finding out that they're not indivisible after all, because he talks about these radioactivity experiments. So at the same time that the consensus was emerging that atoms exist, people were realizing they're not indivisible. And Dalton, at least, wasn't committed to them being indivisible by any means whatsoever. He says they're indivisible, can't be created or destroyed by chemical action. The ether is another thing that people take as something well established. Well, if you look at the history of electromagnetic theory at any given time, up until Hertz's experiments, there's a relatively small group of Maxwellians who think that electromagnetic disturbances are propagated by some kind of medium. In the 1880s, Hertz does his experiments, and okay, by the end of the century, most people are thinking that yes, electromagnetic waves are propagated through space devoided of ponderable matter filled with something they call the ether. And then in 1905, Einstein declares the ether to be superfluous. People usually end the story there without taking into account what Einstein said just a little bit later. By the 1920s, he was saying, and here's a quote, "More careful reflection teaches us, however, that the special theory of relativity does not compel us to deny ether. We may assume the existence of an ether, only we must give up ascribing a definite state of motion to it, i.e. we must take from it the last mechanical characteristic which Lorentz had left it." And he also said, Lorentz's discovery may be expressed as follows: physical space and the ether are only different terms for the same thing. Physical fields are physical states of space. And I think that that's exactly right. That is what Lorentz did. He learned that talk of ether, physical space and ether are only different terms for the same thing. And now I want to show my one slide because I think there's a tendency. Okay, so let me just share my one slide here. This is a passage from Howard Stein's paper, "Yes, but ... some skeptical remarks on realism and anti-realism." And he's talking about the fact that one thing that realists and anti-realists in the philosophy of science tend to agree on is that there were ontological commitments to previous theories that now have been abandoned. And Howard says, "For my part, I throw up my hands to this. Why should we say that the old term ether failed to refer, and the old term atom did refer? Why that is, except for the superficial reason that the word atom is still used in textbooks and the word ether not." He says, "It would be possible to do a lengthy dialectical number on this, but in brief, our own physics teaches us that there is nothing that has all the properties posited by 19th century physicists for ether or for atoms, but that, on the other hand, in both instances, rather important parts of 19th century theories are correct." And I would add that the parts of 19th century theories that the 19th century scientists thought of as being well established have, for the most part, taken to be correct. And I think I published a paper last year about this where I consider, well, I think it'd be, I think we get too beguiled by retention and non-retention of certain words. Do we use the word atom? Do we use the word ether? Who uses the word caloric and who doesn't? I think that it's useful to go back and say, well, what would have happened if we had made the same changes in physical theory, but kept using the older words? So what if in 1905 Einstein didn't say the ether is superfluous, but said what he later said, that what I disagree with Lorentz is whether the ether has enough structure so that it makes sense to talk about your velocity with respect to it. I think it doesn't, he says. I think that there's no such thing as rest or motion with respect to the ether. Then we wouldn't be saying we learned the ether didn't exist. And another thing, I'm not going to go into it now, is that I talk about that paper is, I think that one of the things that Kelvin, and Clausius and everybody else who are developing the kinetic theory of heat could have said was, what we have learned is that caloric is not conserved; it can be created but not destroyed. And I think that that's a more useful way to do it. And I think that that happens also when we're talking about ontology for quantum theories. I think that people get too beguiled by which kinds of words they use. So are quantum states things? Are they laws or stuff like that? I think we should stop and ask, well, what is the real difference? And so I just want to end with a little fable. This is Newton, who is thinking about what it means to be an object. Has a paper called On the Gravitation and Equilibrium of Fluids, usually just called de Grav. And he's arguing against the Cartesians who say that the essence of being a material object is extension, to occupy an area of space. And Newton says something I think is very important. He says, well, there's regions of space all over the place, and some of them are locations of objects and some aren't. What's the difference? And he tells us a little creation story. He says, imagine that God decreed that a certain region of space was impenetrable to other objects. And God decrees that this region of space reflects light. And God decrees that what regions of space have these properties change from place to time and move around according to certain laws. There would be no difference between that and the material objects that we have. Those things would satisfy all the conditions to be a material object. This is why I'm not impressed by talk of ontic versus gnomic views of the quantum state. To be an object is to interact with things in various ways, and that has to do with the laws of physics. We might have an intuition that there's a distinction between a region in space in which there actually is an object and a region of space that just has these properties of interacting with other things in certain ways. But I think if you stop and think about what the actual difference is, there actually is no difference. So the condition we're in is, I think that we are learning about the world. I think that we have good reason to think that whatever the world's made of, something corresponding to quantum states are in the ontology. I don't think that I'm suspicious of views that rely too heavily on one particular formulation of quantum mechanics or not. So you can write down quantum mechanics of particles using wave functions, and you can leave wave functions out, right? You can write down quantum mechanics in a lot of different ways. And I think that we should not be beguiled by one formulation or another, but have as many different formulations of quantum mechanics as we can think of, and think about what they all have in common. Okay, that's it. I'm done.
Okay. Before actually we open the discussion to everyone, do the panelists want to say something? Alexia, Christopher, and the other ones can actually put their names in the chat, and I will take a list. And if I don't see you, please tell me again, because go ahead, whoever wants.
No, actually, I'd be happy to start with the interaction with the audience, to be honest.
Sure. Do you want, Christopher, do you want to? I also already have 2 questions.
I'm good.
Okay, so.
I don't want to say anything more at all, in fact.
Chris, we're not going to let you get away with that.
Okay, wait. It's too much. David, you're first, and I'm going to go. David Glick, yes, sorry.
Okay.
There's too many Davids here. Yeah.
Yeah, so I was expecting more conflict between the panelists here, but it sounds like there's actually a common thread in all 3 of your remarks. So I thought I'd just sort of invite you to say a little more if I'm right about this. And that common thread seems to be a kind of structuralism or structural realism. I mean, going in reverse order, when your approach seemed to be that where we get into trouble in thinking about realism is demanding kind of, or metaphysicians maybe who demand too much, have sort of too ambitious goals when it comes to spelling out the specific details of ontology, so what properties there are, what objects there are, and yeah, if you do that, then maybe the pessimistic meta-induction would come back, right? If you looked at those historical episodes and you said, I want you to pin down exactly what the ether is, then you invite this worry that there's going to be problems. So there's at least something, seems like, well, if you look at what people are actually committed to, and you look at what there's consensus on, you might arrive at something broadly structural. I'll give you a sense.
Yeah. So I think you understood me correctly. One of these days, I'm going to write a paper on what I think about scientific realism and stuff like that. So I'm a very sympathetic, and so this paper that I quoted from by Howard Stein, as I'm sure you know, but maybe everybody in the audience does, that comes from a workshop and was published in the same issue of a journal as John Worrell's paper with the title "Structural Realism: Best of Both Worlds." And Howard and John thank each other in the accommodations. So, and Howard is actually towards the end of the paper advocating something that sounds an awful lot like structural realism, but he didn't coin a word, like he didn't coin a phrase, structural realism, so people kind of overlook that. Now the worry that a lot of people have about structural realism in Worrell's view is that once you get away with from the particular examples that he uses, like electromagnetism, and Howard also is reflecting on the history of electromagnetism, it becomes less clear how to pick out, well, what is the relevant structure, what's the difference between structure and nature and stuff like that. So my own attitude about scientific realism is it's really difficult. So you should you should be committed to the things that you have good evidence for, and it's really hard to say anything more specific about what those sorts of things that those are. So I've called this in the past, this is my incredibly modest proposal. You should believe in the things, believe in what things you have good evidence for, right? And Alyssa Ney, when I was giving a talk at Rochester, pointed out that has a really great, acronym, Wayne's incredibly modest proposal. And so if I'm going to call it wimpy realism when I actually get around to writing this paper. So I'm sympathetic to structural realism, but I'm a little worried that we can sort of like clearly distinguish between structure and non-structure in a way that is general enough.
Yeah, I mean, I guess I'll just maybe say one quick thing about that, which is that, yeah, when you say you commit to the things that we have reason to believe in, even that kind of could be understood in two ways. It could be, well, you might have this idea that in order to believe in something, it has to be kind of fully spelled out metaphysically. And you want to avoid that.
There's just no way that could possibly be true.
Yeah.
People have long believed in the existence of tables and atoms, and no one ever had any idea what held them together. No one ever had even, okay, this is another misconception about the history of science. It's the idea that somehow prior to the revolutions of the early 20th century, there was a clear accepted ontology. That is completely 100% bullshit. All kinds of ideas about the structure of matter kicking around, and they're all speculative.
Alexia, were you gonna?
I just wanted to bounce back on the question of David, because I think he was trying to draw a synthesis between our three presentations. And you, if I understood correctly, you were saying that more or less we were all to structural realists, right? So actually, I'm first going to ask a question to your question, which is for structural realism, is it a synonymous of what I described like relation-based ontology? Is that so?
I mean, it's controversial how to spell it out. Let's say that, but there's definitely, yeah, a relational element that instead of focusing on the specific entities, what there is, a kind of catalog of what there is and their specific natures, we focus on, these more structural facts or relational facts.
That's what I kind of understood. So in some sense, I agree that contextual objectivity, which is what we defend in this approach, we could argue that this is an example of structural realism because there is this structure of reality. We talked about systems embedded in context. But it's important to remember that we also have the advantages of the object-based ontology, where you have these facts that can be shared by everyone at will. So this is a point I tried to make very clear in the presentation. It's not only about correlations. We need this reservoir of facts so that people agree and can talk together.
Right. Is the idea that they can't just be kind of correlations in what we observe? There has to be something kind of in the world, and that's what I mean, because it's relational doesn't mean it's not real, right? You can have. Yes. Something can be 5 feet away from something.
Yes, true. But the danger with quantum mechanics, as I tried to explain in the end, is that if you base everything on correlations, then the danger is that if you establish one correlation between two systems or two agents, and there's the third party that comes into play, then the correlations that were established before, they are ruined. You cannot clone. So this doesn't fit with this idea of facts. I try to explain at the beginning. We need to have some facts that we agree on and that won't be changed if another guy or another interaction comes into play. We need a soil, basically. And that's an ingredient that we bring from the naive ontology, if you like. But I think we can really combine both, because we can avoid being too naive, but still postulate stuff such that we have this field of agreement. Otherwise, we are just going to fight. There is no trust. So,
David, can I try to I really can't compare or contrast myself to either of my colleagues, but the sense in which I wanted to call the Born rule a structural element is this. I imagine in my mind that nature whispers into my ear, use this probability distribution. If I imagined that nature could whisper into my ear the precise probability distributions I should use when practicing quantum mechanics, I would say that's too strong, and I'm left with many of the conundrums that all the interpretations have. It's just simply too strong. So the method of cubism is always to go into retreat and see if there's something that nature could whisper into your ear that is strong enough to make you a practicing quantum mechanic, but not so strong as to leave you with the foundational conundrums. And so the proposal here is that nature whispers into our ear, not the quantum states, not the probabilities, but it says, if you don't use this certain relation between all of your probability assignments, then you will get in trouble. And the idea is that this is sufficiently weak that we have no quantum conundrums, sufficiently weak advice that we have no quantum conundrums, but sufficiently strong advice that we may be able to put the pieces of the puzzle together and say, and ask the question fruitfully, well, why is nature whispering this into my ear? What is it telling me about the character of reality? So that's the idea.
Cool. I'll just say one tiny thing and then I'll shut up, I promise. Yeah, I mean, I guess one important difference between that kind of structural realism and the more kind of standard variety you hear about in philosophy of science, I mean, that's, as you say, it's purely kind of normative. So the constraint is there's a coherence constraint, right? That's grounded in reality somehow, but it doesn't follow that there's any structure about reality. I mean, we don't know, like, why is it that there's this coherence constraint? I mean, if we think about standard probability theory, you know, there's something grounded in sort of logic, right? And, you know, the logic of correct reasoning says that I can't have probabilities that sum larger than one.
Sure.
That doesn't tell you anything about reality.
That's the research project, is to answer why. But now we know where to focus our attention. Why this? So now the question is not why this quantum state, why this measuring device, why this collapse rule. Now the focus is why this relation. And I don't, you know, you and I know each other well enough to know that, I mean, you know, I don't have an answer for that, but I know where to focus my attention.
Okay, I have Davide Romano on the list.
Hi, thank you, Claudio. I have a question for Wayne. The question, can you hear me?
Yes.
Okay. The question actually
is that your question?
No, preliminary question. The question was related to something that came up with Anthony earlier this afternoon, and it's the relation between the nomological interpretation of the wave function in Bohm, and Anthony was discussing with PDBR, but I think I have a problem with the nomological interpretation in a more general sense. So I want to explain what is my problem and see if I get an answer. So I'm totally fine with what you said, that we have to be very open-minded what an object is, that interaction play fundamental role. I'm totally fine. And exactly starting from this, and here is my example. So take just this Schrödinger equation normally. In the Schrödinger equation, we have a coupling between the potential and the wave function. So when we expand the Hamiltonian, there is the kinetic part, the potential part. The potential part is a straight coupling between V and psi. Now, if psi is a field or is an object or is a real entity of any kind, I can say, okay, this is a coupling between fields. And I can understand that this is how physics works. But if psi is nomological, what I have there? So I have a coupling between a nomological entity, something that is part of the law, because usually this is an effective wave function, which is coupled with a physical field, with a gravitational potential, with an electric potential. And the problem that I have with this example is that I cannot figure out how this mechanism works. So, you know, a potential, well, the wave function takes a particular form because we impose a potential on the Schrödinger equation, and then we can, you know, we come out with a wave function. Discussing with some non-logical people like Valia, they were, you know, because my answer was, okay, then take also V as a nomological constraint. Then in this case, you have a nomological constraint between two law-like entities. And some people say, okay, yeah, I can take this, but I think this is not the way that most of the people that endorse nomological interpretation go. I don't think people like Nino Zenghi or Sheldon Goldstein don't think that the gravitational field is something real. So yeah, so my question is, what do you think of this?
Okay, so I think that's a very good question. And first of all, it's important that nomological does not mean not real.
Sure.
It's, you know, it's a matter of fact about what the wave function of the universe is according to these people.
Sure.
And what they're trying to do is, I think this is a mistaken project is, well, let's try to map these things onto concepts familiar from classical physics. And what they're saying is it plays more of the role of a law than it does an object in classical physics. I think that that's a mistake. Okay, but let's think about, okay, think about what happens when we write down a Schrödinger equation with an external potential. I think it's very important fact about quantum mechanics and any physical theory is that even if it has, it's a theory of very broad scope, we are capable of using it to model not something that is not the entire universe. And typically when we do that is we'll treat a subsystem of the universe as the system of study and subject it to exogenous fields. Now, like a magnetic field, right? Now, of course, when you're subjecting an atom to a magnetic field, what you're doing is you're turning on your electromagnet and putting it there. So there's this other physical system, right? And then if if I modeled the big system consisting of my atom and my electromagnet, then that would be that potential that showed up as an external potential in the original version would just be part of the law according to which the wave function of the whole thing evolves. So like one of the things that's different about a wave function in ordinary quantum mechanics and a law of nature is that there's a law of evolution of the wave function.
Mm-hmm.
Now, there's no particular reason why in classical mechanics you couldn't also have evolving laws of nature, but we don't, right? So one of the things that if you're thinking of the wave function as itself having a law-like relation to the particles in the sense of telling them what to do, there's also a law about the wave function. In ordinary quantum mechanics, how it evolves. Now, what they want to do is have a Wheeler, the wave function of the universe really be a solution of the Wheeler-DeWitt equation and actually have it be static. But then the effective wave functions of bits of it can evolve. But even if the wave function of the universe is static in some sense, then there's still a law about what that thing is. So it's still subject to a law. So on the gnomic view, there's a sort of hierarchy. There's the particles that are subject to a law, the wave function tells where to go. And then there's a meta law that says either, this is how the wave function evolves and, or, here's the one possible wave function for the universe.
Sure. No, I agree with the picture. Now, yeah, I don't want to take too much time to other questions. So, but let's say for me, it remains the problem to understand how something which is part of evolving law couples with the field. I think to do this in a consistent way, one should either take both as nomological or both fields, but maybe we can discuss it further in other occasions.
We have time, but we also have a few more questions. So,
okay, I mean, if Wayne want to reply on.
Yeah, no, exactly. So Wayne, if you want to.
Oh, so I'm not sure I know what I mean, I don't think I have anything to add. Putting the potential in as an external field is just an artifact of the fact that you're not modeling the source of the field in your theory. In the if I include the source of the field, then there would be just the various particles and photons and things like that. All of that's in the quantum state, and
Okay.
right. So so it's an electromagnetic field. Well, okay, what is an electromagnetic field? Well, in quantum field theory, we model it as a collection of like a state of the electromagnetic field is a particular quantum state in QED, right?
I understand what your answer is. Okay. Okay. Thank you very much.
But also like actually, I want to push back on this. What you said at the end, like, I don't know how to how to make sense of should I think of this as a law or think of something as a field? Well, what's it mean for there to be an electromagnetic field in a certain place? It means that, or like if you look at the beginning of the field concept, it goes all the way back to Newton. Actually, he says it's a property of a region of space that if there were a particle placed there, it would accelerate. It would have a certain force, and that's what a gravitational field is.
Right.
It's an assignment of these counterfactual forces to every point of the thing, and or an electric field or something like that. So I actually don't know the difference between. Is that a law? Yes, it is. Is it right?
I see. Okay. Yeah. Thanks, Wayne. Yeah. Thank you very much.
Wait, gentle. Yeah, okay. Chris Simpson says a gentle challenge on the PA arguments by Chris, which is wonderful. But first I have Aurelian on the list. So.
Thank you. So thank you. So my question is for everyone, but I will ask the question to Wayne because it's somewhere between the different part in the discussion, so maybe everyone can answer, it doesn't matter. So my question is about the common structure that you mentioned, Wayne, about the common structure between the different theories in interpretation, discussion of quantum mechanics that exist in the literature. And I think it's very central to emphasize the point that okay, we can have common points between different discussion and interpretation of quantum mechanics, but it's also we have differences. So I think the differences will make the difference at the end. So if you can't find something that it is on just a transformation from one theory to another, so it's like translating books. I think it's not so much fascinating that to translate a book from language to another. Of course, it's nice, but it's we expect something more. So maybe the motivation for all this approach is only for the future if we can get something better. Otherwise, we'll go in a circle. And so the reason why I like the two proposals that of the GRW first on one side, because it's a kind of theory which is proposing something new. It could be test experimentally. Okay, that's it's difficult to say, but what I like more is the point of view of the Breuer-Bohm, because it's connected to the past. So you have you have all the tradition of the history in the past. So trajectories and dynamics, Hamilton-Jacobi, etc. And you have possibility to think about the future. So because it's this in that framework, for example, if you ask somebody like Anthony Valentini, will tell you that you have no Born rules as necessary requisite. So it's like what say Christopher, if Born rules is not so essential for Bornian mechanics. It is a consequence of something that you have to assume, but is not postulated from the start, and it cannot be derived. So yes, there are future things to do, but I'm believing that you have to go a bit beyond what we have actually. And I'm not sure if...
Okay, so let me just say what I think. Okay, so I think that what we should be committed to about what there is in the world is what we have good evidence for. And I do think that we have good evidence that quantum states correspond to something in reality. And that is something that the Bohm theory and collapse theories and many worlds, and I would argue the relational quantum mechanics actually do in fact have in common. Now, what question is, do quantum states always evolve the way our current quantum theories tell us to? Did they always evolve unitarily, or could they be, subject to some kind of stochastic evolution of the type that Angelo? Right? I think we should be open to both possibilities, and I think we should push the collapse program in exactly the way that people are doing to potentially find evidence for departures from unitary evolution. So, what we should be committed to, I happen to think that what we actually do have good evidence for is something that it is in fact something that these various so-called interpretations have in common. But the reason I put interpretations in scare quotes is they aren't interpretations of a single theory. They are distinct physical theories. If there are quantum states in the world, then there's a matter of fact about how they evolve. And what these tests of collapse theories are doing are telling us something more about how they evolve, putting constraints on viable laws of evolution. In terms of Bohmian mechanics, Anthony, as Anthony has emphasized, and this is something that Goldstein et al. Don't, a hidden variables theory like Bohmian mechanics or something like that actually opens up possibilities that aren't possible without these things, possibilities of non-born rule statistics. And as you know, Anthony has spent time asking could there be evidence that there was that sort of thing in the early universe? So yeah, these are distinct physical theories, and I don't think we should be committed to. These are distinct physical theories which all agree on probabilities for outcomes of experiments within the domain which these things are being tested, but they're distinct physical theories. So what I think what we should agree on, what we should be committed to is, yeah, ordinary quantum mechanics gets those probabilities of right within its domain of application. We should be strongly committed to that, and I do expect that to survive theory change. And yeah, then push to see how do we go beyond ordinary quantum mechanics, exactly in the way that the collapse theorists and Valentini and other people are doing.
I wouldn't mind reacting to Wayne briefly.
Okay.
Particularly to the statement that you believe there's so much evidence that quantum states should be understood ontically. I would say exactly the opposite. There is so much evidence that, to my mind, that they should be treated epistemically, that's the research program to approach. Here's where I think there's a distinction between us. And so let me try to spell it out. What I would say is there's overriding evidence that they should be understood epistemically. What the PBR theorem teaches us, and what Bell's theorem teaches us, and what some of the other no-go theorems teach us, is that if they're understood epistemically, they should not be understood as epistemic about quantum states. So you think that the PBR theorem is a strong piece of evidence that a quantum state should be treated ontically, whereas I'd say no, all it means is, for instance, that your assumption number 5 was on the wrong track. They're epistemic, but not epistemic in terms of the Harrigan and Speckens, what do they call it, ontic model framework? Yeah. So, and you know, and I don't know exactly what Rob thinks of that, but PBR themselves think that that's what they've shown. And Matt Pusey, for instance, when he gave the talk that I know you were at Western, Cubism 80% or 20%, you can see that he has leanings toward Cubism, so he doesn't think it demolishes Cubism. But on the other hand, I've seen Tim Maudlin say, I don't care what they think they've proven. I will tell you what they've proven. And so I think that's your strategy. And I think it's just that you don't want to draw an appreciation that there can be epistemic states about something other than ontic models.
Okay, this is good. Yeah. Notice I didn't use the phrase epistemic state at all, ever.
No, you didn't. I apologize.
Yeah, right.
And
yeah,
may not use ontic, but
right. Yeah,
yeah.
Harrigan and Speckens use epistemic just as a negation of psi epistemic just as a negation of psi ontic, and I don't like that terminology, so I avoid it. Right. Okay. So all right. So this is good. So as I said, I think that the research program of thinking of okay, so if someone says that quantum states, there's evidence that quantum states should be thought of as epistemic, then yeah, then the obvious question is, well, what is it that you take to be that evidence, and then let's evaluate that evidence. So right. What is the evidence?
Evidence things like this: quantum teleportation, quantum superdense coding, the no cloning theorem, the no broadcasting theorem, the existence of a quantum Di-Finetti theorem.
Right.
You know, I can list you dozens of things that I count as evidence.
Right.
Of course, they're not experimental evidence, the kind that Angelo is looking for, but conceptual evidence. You know, there's any number of things that you can look at other than a single isolated no-go theorem.
Okay, good. Yeah, good. This is really good. So, you know, as I said earlier, I think that this project of pursuing, you know, Einstein's goal of thinking of quantum states as like classical probability distributions, it's a shame that it was kind of dropped and left aside, because I think there's a good general theory, as you know, there's this, general probabilistic models in which you can prove those kinds of theorems that you just mentioned, which were all originally, for the most part, arrived at within the framework of quantum mechanics, within a more general framework that includes, theories in which there's, indistinguishably built into the of states built into the ontic structure, and theories where no indistinguishability is just overlap of probability distributions. And most of those things that you just talked about are consequences of having pure states of the theory that are indistinguishable. I didn't catch the whole list, but most of them are. So you could say, okay, here's we've got this general theorems about theories that have pure states that are indistinguishable. And there's two ways that they could be. They could be, it could be epistemic indistinguishability, but it could be built into the structure of the ontic state space. Or you can, maybe say we shouldn't be talking about ontic state spaces whatsoever. And so these theorems apply to everything in that class. And then we start to look, okay, now, is there a way to distinguish between these kinds of theories? So can we think of quantum theory as, just like a classical probability distribution? Then you start to look for theorems which distinguish within that class of theories that have pure states that are indistinguishable.
Well, let me throw this in at this point. I've always loved one of the little paragraphs in Rob Specken's toy theory paper, where he says, could you give a realist explanation of no cloning? And he said, likely. Could you give, or I don't know exactly what term I want to use, ontic or realist. Could you give one for quantum teleportation? Very likely. Could you give one for, and he put a large list down.
Right.
And then he said, my sense is that for each one would have to give an ad hoc explanation. Whereas at the cost, so for those of you who don't like the epistemic notion, whereas at the cost of recognizing that quantum states are epistemic, one can give a unified explanation for all of these phenomena.
All right.
To the physicist, that's a compact, useful idea, that if you can give one single explanation, no matter how hard it is to gulp for so many diverse phenomena, then it's a pragmatically useful, and maybe I shouldn't even say pragmatically, for those of us who's, well, it shows you're on the right track. Whereas if you have to invent a new model for every little piece of quantum theory, and maybe you still haven't found a good unification of it all, then fine, you've shown existence proofs, but they're not very convincing from that point of view.
Okay, so I don't want to, there's other questions waiting, so I don't want to belabor this, I think that I would have to, I don't remember exactly what Rob's list is, but I think that a lot of those phenomena could be encompassed like within this general framework, which could include, theories with probability distributions that overlap, and also theories with, with genuine chances in them. I think a lot of those things, the unified explanation is that you've got pure states of the theory that are not distinguishable. Now, I don't know that all of them can be of that. And that's relatively neutral as to the reasons for the indistinguishability. But what I want to say is, okay, that's but I want to distinguish between two questions. If you said that's a very pragmatic reason for taking these things seriously, or I forget exactly what you say. That's absolutely right. And this motivates a research program on which quantum states are like classical probability distributions. I agree that was a well-motivated research program. And one of the reasons to pursue a research program is, it can learn, it can be valuable no matter how it turns out. We can, like pursue a project of trying to construct a theory of certain kind and end up with a theory or find out that it doesn't work. And I think that the no-go theorems are fruit of that project. So it's been a very fruitful project.
So should we, I don't know, I'm looking at the organizers here. So we have still 2 questions. Let's just move. Alberto, you're up.
Thank you very much. First, I wanted to thank you, the panel, and the organizer. Very, very interesting exchange and discussion. I had a question for Chris. I don't know if you can say a little bit more at conceptual level of the relationship between what you showed, variation of Born rule, the SIC problem, and the 12th Hilbert problem. And if any concept there helps you to think at the Born rule in a new way.
Well, the thinking of it in the new way is, so the general conception is that one starts with quantum states and measurement operators and combines them and gets a probability. So from the usual presentation of it, logically prior to the probability, conceptually prior, logically prior to the probability, is this entity called a quantum state and an operator that describes the measuring device. That then, I think, through the kind of reasoning that Harvey Brown uses in the paper that I was citing, leads you to think, fine, you can get probabilities from quantum states, but they have more structure than simply probabilities. So in a certain sense, you've deleted some information about the states by calculating probabilities from them. What the kinds of expressions in the d² double slit experiment shows you is that you can find an expression of exactly the same rule, the Born rule, but is purely in terms of probabilities through and through, both on the left side and the right side. That takes you down the conceptual or the path of thinking, well, if there's probabilities both on left and right, which are the logically prior probabilities? Which are the more important ones? Which are the physical ones and which are the epistemic ones? If you give up that distinction and say, no, they're all on an equal footing, then it gives you a way of thinking of the Born rule that isn't just about inputs of physical properties leading to probability assignments, but instead a relation between all probabilities. So that's the first part. So it gives you a new way of thinking of the Born rule that only involves probabilities. There's no complex numbers anywhere. But then it actually turns out that the complex numbers are hidden in the story after all, not in terms of having entities that are different than probabilities, but in the range of possible probabilities that one can adopt consistently with that equation. So ultimately, as opposed to someone who said the Born rule is derived in other interpretations, actually, I would like to start with the expression that I showed you, if I could, and derive from it all of the rest of the structure of quantum theory. In other words, don't start with states and operators, but start with this relation and get the whole story of quantum mechanics, including complex vector spaces and positive semi-definite operators and the tensor product rule, all of that from the assumption of the Born rule, which is a very natural assumption from this Bayesian approach. Rather than having assumptions about things that are not probabilities, start with assumptions about things that are probabilities. All right, now in an effort to clean that up, and find a good starting point, we tried to look for the minimal distinction between the quantum rule and the classical rule as normally conceived. And you can prove a lower bound on the distinction that is achieved if and only if a certain symmetric structure can always be found in all quantum state spaces. And then that's where it gets hard, because no one has ever been able to prove that these things exist until recently. One of the conjectures has been reduced to an instance of Hilbert's 12th problem, which is fatal in certain ways, because Hilbert's 12th problem hasn't been solved. So it means you've got to either be patient or insane, or you've got to take one of the routes that Schrodinger called a fake direction, an easy way out, just so you can say something in your lifetime. My inclination is to hold out. We have a way of thinking of the Born rule that says, think about these structures that were hidden, a hidden symmetry in quantum theory for 100 years that was never noticed. And maybe, it's a hope, maybe that symmetry will be the right thing to latch onto to get a stabilized notion of what quantum theory is telling us. Previously, Everett, Bohm, they were based on an understanding of quantum mechanics. Well, I mean, GRW is a very good example of one that is based on a particular representation, a particular way of thinking about quantum mechanics. You know, it can be reinterpreted to work in the way that I'm writing quantum mechanics, but it no longer seems natural. Maybe it never seemed natural. It never seemed natural to me. But with hindsight, one can always take all of the interpretations and turn them into each other. My question is, with foresight, which interpretations give you foresight to move to new levels of things? I don't know if that was your question, but but thank you for the opportunity to have a soliloquy.
Could you just say a little bit more on how the reduction is made and if there is a place to read about it? Because the reason I'm asking is that the 12th problem is not solved in general terms, but there are a number of cases that are known, and it shows that there is a link of certain structure with the hyperbolic structure, which are typical of the Lorentz group. Effectively, you're saying that there's something of the Lorentz group hidden in the Born rule, and that's a bit it's a bit fashionable if you want, but it's interesting.
For instance, one instance of Hilbert's 12th problem is extending the rationals by imaginary quadratic fields.
Yeah.
So Kronecker and Weber and other people who built on it completely characterized those fields. So rationals extended by a pure imaginary number times a root of a
quadratic.
Okay, one instance that has not been solved is extending the rationals just by real quadratic fields. And this problem is reducible to that question.
Okay, so is connected to the real quadratic problem.
Yeah. So I mean, what does that tell us about physics? I really don't know. This is the kind of thing that we make a little headway, and then if we do, and then Renato Renner will turn his attention to it and then do something really useful with it. But you know, it's just a hunch that there's a relation between the simplest possible re-expression of the Born rule and this deep mathematical problem.
Yeah,
strikes me as telling us something.
Is there anywhere I could read a bit more about?
Yeah, why don't you send me an email and I'll send you a list.
Thank you very much.
Sure.
Good. We're almost out of time, but we have, so we'll finish on a high peak, on a high note with the question from Guido.
Okay, thanks. This is a question for Chris again. And I mean, you were emphasizing how cubism is a quest for ontology, and the sort of openness of this quest. And since we're friends, I can be rude to you, and I want to turn this against you. I want to say,
well, you'll owe me single malt the next time we meet each other if if you still collect them.
I mean, you showed us these beautiful examples, rethinking the Born rule, the Seek POVM, research program, and so on. And all of that, I can see comes from the commitment to the subjectivist notion of probability, the personalist Bayesian idea. I can't really see where in the program you have to rely on denying that quantum states, Hamiltonians, POVMs, and so on are ontic, as opposed to denying that the quantum probabilities are objective. So I would like to sort of urge you to really keep it open. What's the ontology that we are after? Well, yes, we do have some evidence that quantum states are real, some evidence that they're not. Who knows? And what's crucial to cubism is the subjectivism about probabilities. And that's been hugely fruitful. And please continue. I love your work. But why say that quantum states can't be ontic, or Hamiltonians can't be ontic, and so on? Just say they have nothing to do with probabilities. Probabilities are in our head. And what the right ontology for quantum physics is, we are in the business of finding out.
So a lot of it is based on a hunch, but I've told you many of those hunches before, but let me put it in the context of today's talk. The Born rule was rewritten in terms of a relation between three probabilities. So Q of dj was probability of the far measurement outcome, the far measuring device that's much like the screen in the double slit experiment. On the right-hand side of the equation, there were two other probabilities. One is an unconditioned probability, and the other one is a conditional probability. If you want to have a consistent Bayesian notion, personalist Bayesian notion, then you should accept that all three of the probabilities in that equation are personalist Bayesian probabilities. Okay, so let's say you accept that. I mean, maybe you don't, but let's say you accept that.
You can quote me on that. I'm very happy with that.
All right. On the right-hand side, the P of Rj, the probabilities for the reference measurement outcomes, completely characterize the quantum state. If you know that probability distribution, you also know rho, quantum state. They're completely equivalent. If you know the P of Ej's given Ri in the equation, the conditional one, if you know that collection of conditional probabilities, it completely characterizes the measurement. So now you're pushed in this direction. If A, you've accepted that all probabilities are personalist Bayesian, then what are you to make of the fact that two of these probabilities in this relation completely characterize, one, the quantum state, and two, the measurement operators? So this is only one among many arguments I've given, but and perhaps none of them are completely convincing. But if you take the sum total of them, I find it very convincing. But now methodologically, one further thing. Why not let 1,000 flowers? What is the phrase?
Bloom.
Why not let 1,000 flowers bloom? This is also a methodological consideration. I think it's fine that Angelo, for instance, pursues his research program, and the other people do theirs. From my own perspective, I would say what we're doing is we're in the business of clearing the underbrush, clearing the things that cloud our view from the real stuff. And it has always struck me ever since the first consistency arguments that we made 20 years ago now, it's always struck me that we stand a better chance of progress if, at least for our own personal research programs, we don't let 1,000 flowers bloom. We hard-headedly pursue one direction, and Darwinian natural selection will either let us proceed or it'll stop us. So that's my personal reasons for not being liberal or agnostic on this issue.
I mean, if I can come back, Claudio.
Look at the organizers. We have 5 minutes more, guys.
I think, yeah. I mean, if there is a last point, just to make.
Go ahead, read them.
Yeah. Still, I don't. I mean, two things. I mean, I still don't see what's crucial to your research program beyond the subjectivism. Why you feel you need to insist that quantum states, Hamiltonians, and so on are not ontic. Why is that crucial to what you're doing? If and then you've given me an argument why you feel, I mean, it's a hunch, that you've said that these subjectivist probabilities fix the quantum state. But the fact that these probabilities mathematically corresponds to a quantum state doesn't mean that they are the same thing. The same is true in Bohm. The same is true in Everett. Take the Bohm theory. Probabilities are like in classical statistical mechanics. You can be a subjectivist about probabilities in Bohm, but the quantum state is real because it's a pilot wave. It's pushing particles around, and that aspect you may not believe in Bohm, so you don't believe in that particular aspect of the quantum state, but it's logically independent of the probabilities. In Everett, the quantum state is real. It's the stuff worlds are made of, but in the way that David Wallace thinks of probabilities, probabilities are subjective. yeah, he has an argument, why it makes sense to numerically choose our subjective probabilities, equal to the weights in the ontic wave function of the universe. But again, conceptually, they are two different things. So I think you can do the same. Just take Bayesian personalist probabilities and treat those as logically independent of the question whether there's actually something out there that's the quantum state could be whatever sort of I mean just think of the ground state of the hydrogen atom as a value of energy. Or David Wallace was talking about the sky being blue, and everything we use to understand that doesn't really have to do with probabilistic predictions in measurements. After Chris Timpson's talk, I mentioned when Born introduced the Born rule, matrix mechanics was already there. The idea that these are this is the right kinematics of the world, and talk about sort of values of observables. That was stuff that they all accepted before introducing probabilities. That's what I'm saying. It's possible to consider these as logically independent, and I think the probabilist, the personalist probabilist aspect is absolutely crucial to what you're doing. I don't follow the logic of having to deny necessarily. Maybe you're right, but I don't see that it follows that you should categorically deny that states, Hamiltonians, and so on are ontic. I think that's still compatible with what you're doing.
I agree.
But you want to say the last few words?
Oh, I don't know that it would do any good. But I would like to hear, so I won't say the last words. I think Guido should say the last words. I want to.
I mean, I've said what I wanted to say.
I'd like to see how he reacts to this. If you take the formulas that I introduced today, and you start from the end of quantum mechanics. So take your objective Hamiltonian that you want, your ontic Hamiltonian, and plug it into the expression for two instances of the reference measurement. If you plug the objective Hamiltonian into that expression, that gives a unique probability assignment for the conditionals, the conditional probabilities, unique. Now, suppose I walk up to the system and I say, I'm not adopting that probability assignment. I've got reasons for adopting other conditional probabilities, internal reasons. Now, the personalist Bayesian wants to allow that there's nothing in the world that makes his internal probability assignment right or wrong. But if you've got your objective Hamiltonians, now the possibility is open that his internal probability assignment is factually right or wrong. That's the thing I'm trying to guard against. I don't see how you can, and I leave you the last word. I won't say anything more. I don't see how you can get around that now that a mapping has been made between all of the entities and probability assignments.
I'll just say this. Yeah, a subjectivist Bayesian is generally going to adopt, I mean, subjectivist Bayesian might, adopt, a completely new set of probabilities, anytime they want. Most subjectivist Bayesians will also have some kind of theory, that they model, sort of working model, call it however you want, that sort of guides them, in choosing their probabilities. And okay, if your subjectivist Bayesian, is somebody who uses quantum theory with ontic Hamiltonians, as their sort of manual, as their guide, in setting their subjectivist probabilities. Okay, then they will be more constrained, if they've chosen one set of probabilities at one time, and then they believe that the Hamiltonian is ontic, and they should take it seriously in their theory. Then they'll be constrained about the probabilities at a later time. But I mean, that's still their free choice, because that's the theory that they choose to adopt. It's just a self-imposed constraint, but so it doesn't contradict the fact that they're actually free to choose whatever probabilities they want. It's just that this is a scheme that they find useful in as part of their strategy to navigate the world, to consider Hamiltonians as ontic, and that structures a bit more the way they assign probabilities.
Okay, I think we should stop here. Also, I did detect, right, some sort of Shakespearean quote from The Tempest, right, before the stuff we're made of was not. I thought that Shakespeare trumps quantum mechanics, so we should just stop here. Shakespeare always does that. But before we go, can we actually thank all the speakers, and especially the organizers, which have done an incredible job. So Cyril, Alexia, Vincent, and Chris, really, that was incredible. I don't know how you pulled it off. And it was fantastic. And if you guys want to say the last words, just to say.
The last word is just to say that once again, all the credit goes to Christian. Yeah, he's really the one who made it possible. So thanks a lot.
Exactly. Thank you to Christian.
Thank you, Kristen.
Very much.
Thank you, everyone. If I may say just one thing, thanks a lot to everyone, the speakers, Claudio, Giuliano, and the other, Hippolyte, Richard, Laurie, which had the sessions, along with Cyril and Vincent also. And I wanted to thank the scientific committee, which we never mentioned actually, but we've been exchanging emails to decide the program. So actually we decided together the program, and it was really everyone was really helpful. So Guido, which you have been hearing in these days, Hans Briegel, Jeremy Butterfield, Chris Fuchs also was there, Nicolas Gizen, and of course Vincent, Cyril, and Alexia, Klaus Molmer, and Eugene Simon Polzik. So that was the scientific committee, which I wanted to thank. And that's the only thing I wanted to say. I wanted to thank them for allowing me to, organize, and it was really nice. tiring but nice. Now I'm going to drink a couple of beers, I guess. And yeah, in the next few days, I'm going to send you probably the last few emails, and then you're not going to hear from me again about the recordings, which are going to be online fairly soon, I guess next Monday. And plus possibly about proceedings, if this is doable. We will see, of course, with the speakers. So yeah, that was everything. Thanks again to everyone.
So
Please leave